All right, let's get started. So kind of made a little bit of a judgment call. So we've been doing logic, and it makes sense to end your logic with set theory. But since we're also going into topology, it makes good sense to start topology with set theory. So it's completely arbitrary, but I'm going to start calling this course a topology course now. I'm going to start a new playlist, uploading the videos to the topology playlist. I'm going to consider this not the end of logic, but the start of topology.
Okay, so last week was the end of logic.
So last week turned out to be the end of logic. Celebration. You got through logic. So since we're jumping into topology, might be appropriate to do a little bit of high-level intuition for topology. Kind of did this informally after class last time, but let's get it as part of the actual lecture. What exactly is topology from a high level? Topology from a high level is a study of proximity. Study of proximity. So going back to geometry, we care about a lot more than proximity. Geometry, the main relation we use in geometry to talk about things somehow being the same. Each field of mathematics, it has its sameness relation that it cares about. With sets, we'll get to it, but we care about sets being isomorphic to each other. Same with if you do abstract algebra, you care about algebras or algebraic structures that are somehow isomorphic to each other. In geometry, what we cared about were structures that were congruent to each other. They were somehow the same. And so we have the notion of one triangle being congruent to another triangle. Now, what did it mean for two triangles to be congruent? That side's the same as that, same length as that side. This side's the same length as this side. This side's the same length as this side. This angle's the same big as that angle. This angle's the same big as that angle. This angle's the same big as that angle. This thing's area is the same as this big as this thing's area. It has a lot of structure that is the same. And so this sameness relation in geometry of congruence preserves a ton of structure. Let's talk about a lot of structure. In topology, all we're saying is two things are the same. We'll use the same squiggly line. In topology, this time we're calling them homeomorphic. You'll learn some big words that make you sound cool. Hopefully you don't suffer from, what is it? Hippopotamonstros squiptoliophobia. Fear of big words. I think that's right. In topology, these two would be the same and have the same topological structure. They have the same topological intuition for what the same topological structure means. Is we always think about in terms of rubber bands. If this were a rubber band, I could reform it into this shape and proximity would be preserved. If I had the rubber band and this atom was right next to this atom over here, when I stretch it out this way, those two atoms are still right next to each other. So I can take a rubber band, any two atoms that are next to each other, physically touching is what we'll mean by close. That's intuitively what we mean by close. Two atoms being close to each other when I have a rubber band are still close to each other when I completely stretch it and pull the rubber band like that, as long as I don't deform the rubber band in the process or break it. And yet, the distances between them, between all sorts of points, could be drastically different. Right here, maybe this point and this point, before they were an inch apart, and now maybe they're over here 3 inches apart, or whatever. Topology doesn't care. So we don't care about distances. All we care about is proximity. And there's a property that comes up a lot in proximity, or a lot in topology, that it turns out is a property that we only care about proximity for. A notion, and that's the notion of continuity. You have a high-level notion of a continuous line. Is this line continuous? No, because it has a hole in it. You want it, in some sense, to not have any hole in it. Now that's a continuous line. And it turns out the notion of continuity is this notion of every point kind of has that point that it's right next to. And so we have this notion for continuity when we're talking about on the R2, on the geometric plane, the real number plane, whatever we call it, the Cartesian plane. But can we have a notion of a continuous function from, I don't know, the set ABC to the set 1, 2. Can we create a continuous function that maps from here to here? We know how to do it from the real numbers to the real numbers, and that's real easy. Just don't pick up your pencil and you're good. But is there some notion of proximity that works even for sets like this? Or some notion of continuity that works for even sets like this? And the answer is yes. So continuity is a property that comes up as a result of topology a lot. And it turns out we can talk about continuous functions in lots of cases. And the continuous functions that you're used to on the from the real numbers to the real numbers is just a special case of a special topology on the real numbers. And so what's a lot of your analysis, those of you who have done like calculus, obviously continuity is one of your 4 major ideas in calculus. What you're really studying is just a special case of a particular topology. We call it the standard topology on the real numbers. And so that's in some sense a special case of topology. So topology is more broad, more fundamental. It's a very basic field of mathematics. And then it's considered one of the 3 major fields of pure mathematics. The 3 major fields of pure mathematics being algebra, analysis, and topology. So that's a little bit of dipping our toe into topology. What are we going to do in this class? First, we're going to develop set theory. And then we're going to do prelude stuff, which is like introducing you to notations, relations, functions, a bunch of stuff that's going to be used throughout the class before we get to topology proper and define what an actual topology is. So today we're focusing on set theory. The next time we'll get into relations and functions and just introducing you to notations. This one's going to be kind of an annoying step because it's going to feel like we're kind of just vomiting up all this notation on you. But that notation will only actually slowly use throughout the class. So we're going to vomit it all up on you once and then slowly reintroduce it as needed throughout the class. Rather than just, as we go throughout the class, drop a notation on you that you've never seen before. So that's a high level how the class is going to go. So today we start with set theory. Set theory, we've got 9 axioms here that we're going to cover. The first 2 axioms are kind of our existence axioms. They tell us that sets exist. Our next axiom is going to be an axiom that introduces this bracket notation that we know and love for writing sets. Our next axiom is going to be an axiom for how we union sets together. Our next axiom is going to be our axiom that gives us our set builder notation. You know, you're used to the set of all x such that some condition about x is met. And then our axiom after that, we have an axiom that introduces the power set of a set, the set of all possible subsets. Then we have an axiom that introduces the natural numbers or infinity. Then we're going to have a weird one. It's called the axiom of choice. That's one that we hardly ever use. We're only going to prove one thing, I think, in topology that actually depends on that axiom. So not a particularly crucial one that's often skipped when people do set theory. And then finally, our last axiom is an axiom about types of sets that we can't have. So those are 9 axioms we have. And we'll jump into each one, trying to give plenty of examples as we go and creating definitions as we go. So everything's well defined. We're going to kind of rigorously define things, and then from there on out, we're going to say, okay, now we're going to be a little bit fuzzy with it. Rigorously defined, and then we're going to be a little bit fuzzy with it. Because it turns out being rigorous the entire time turns into kind of a pain. But so starting with the rigorous part. First axiom, axiom 1. The expression x is a member of y is a proposition. What's a proposition? Something that's true or false, but not both. So x is in y. If that's a proposition, then that means that thing right there is that symbol is a predicate. It's a particular type of predicate because it's taking 2 things.
Giving the truth or falsity.
Yeah, this is either true or false. This is a proposition. So that symbol is it's a predicate, but it's a special type of predicate. A relation. It's a relation. A relation is something that takes 2 terms and spits out true or false. That's what it does. This is one of our primitives. We will not define this symbol. So primitives, this symbol is one of our primitives. By the way, that's a Greek letter epsilon. I'll draw it kind of big there once for you to see it right. That's what it looks like. And then I'll probably have a bunch of awful drawings of it.
You write all the other primitives for us?
Yeah. So It's going to be a big list. Here's our first primitive. Here's our second primitive, a set. All right, those are all our primitives. Set and is a member of. We often call that the is a member of relation, or is in the in relation, or whatever. So, little bit of thing that's going to bother your intuition if you've already done a lot with sets before. The only thing we're putting in sets are more sets. We're just doing sets of sets of sets of sets, and everything sets. All our objects that we talked about always and forever in this class are going to be sets. And we already talked a little bit at the end of logic about how you can define any mathematical object you can think of as a set. The number 16, it's a set. A function, it's a set. A relation in mathematics, a set. A square, it's a set of points. What's a point? It's an ordered pair. An ordered pair, we're going to see how we define an ordered pair as a set. Everything's sets. And all we got inside the sets are sets. That's it. Okay. So the expression x is a member of y. This set is inside that set. It is a proposition. It is something that is true or false, but not both, if and only if x and y are both sets. If x and y are sets, I'm guaranteed that that expression is either true or false. Furthermore, if this expression is either true or false, x and y must be sets.
Okay.
Make sense?
Yep.
Okay. Let's see that in a little bit of our notation, a little bit more precise notation. For all x and for all y, it's understood now that since we're in the context of set theory, for all x means for every set x, and for all y means for every set y. We're only talking about sets here. So for every set x and for every set y, we either have x's in y or not x's in y. Now this is the exclusive or, not the inclusive or, so we put that line above it. Exclusive or means one and only one is true. The inclusive or means at least one is true. The exclusive or means one and only one is true. That's the exclusive or. We're saying one and only one of those two things is true for any two sets, x and y. Okay, now motivate this a little bit. Why this axiom and why this weird specification? The expression x is in y is a proposition if and only if x and y are sets. This was an axiom that actually took a good amount of time for logicians to come up with and for mathematicians to come up with. And one of the things that motivated them coming up with it is what we call Russell's paradox. Now, prior to this axiomatic development of set theory, if we went back to the year 1900-ish, two people by the name of Russell and Whitehead wrote these massive textbooks thoroughly laying out set theory and constructing math from set theory. They did a lot of the work for constructing math from set theory. They developed what we often call naive set theory. And they enabled us to kind of be a little bit fast and loose with what we call sets. And so I'll give you an example of one of the sets that gave them a lot of headache and made them realize their system just doesn't work. And Russell, if you read his book, History of Philosophy, he talks about how they came across this set. Talks about how he'd wake up from nightmares of students throwing his texts out the window and burning them, or something like that. He hasn't realized, it turns out a lot of that work, it went down the drain, but not really, because once we do rigorous set theory, we use the parts of naive set theory that we can do. Naive set theory is more of the hand-wavy stuff. It really helps us with the hand-wavy stuff, which is convenient, just not rigorously correct. So let's see how hand-wavy stuff can get us in trouble. Let U be the set of all sets that don't contain themselves. In other words, what's U? For every set X, if it is not the case that X contains itself, then X is in U. That's how we're defining U. U is a set of all sets that don't contain themselves. Let me give it to you in set builder notation. U is equal to the set of all X such that X does not contain itself.
Okay.
Set of all sets that don't contain themselves. Good? Seems like a pretty natural thing to do. Just from a basic set builder notation, looking at that, it's not obvious anything's wrong. But let's ask some questions about this now. Question. Is U inside of U? Well, either one of two possibilities. Either it is or it isn't. Right?
Yeah, but it can't be
All right, so let's say that U is in U. What does that mean? Well, U is a set of all sets that don't contain themselves. If U is in U, then U is not in U, because U contains itself. If U's in U, U contains itself, but U is a set of all sets that don't contain themselves. So that would imply it is not the case that U is in U. Okay, contradiction. That must mean that U's not in U. So is it the case that U's not in U? Well, if U's not in U, and U's a set of all sets that don't contain themselves, then that means that U is in U.
And then it's just
Right, so if it is, it's not, and if it's not, then it is. What's the solution to this?
doesn't work.
What do you say? Well, we found a set that doesn't work. Ignore that one. Go back to Axiom 1. U isn't a set. It's a set, X and Y are sets, if and only if this is a proposition. This has to be either true or false. Using U, true or false? Bad question. It's not a proposition.
You can't say X
So-
is X.
So U is not a set. Naive set theory allowed us to do stuff like this. We had to come back and refine it and be more strict, more rigorous, make more explicit exactly what we can and cannot do. And so that's largely the motivation for this first axiom here.
Can you go over that again? I'm not catching on. Why does that not pertain to Axiom 1? Or how does Axiom 1 pertain to that situation?
Axiom 1 says, the expression X's and Y is a proposition, is true or false, if and only if X and Y are sets. So in this concrete example, U is in U is a proposition, if and only if U is a set.
And in Russell's paradox, he's saying U is not a set?
Well, is U a proposition? Let's ask ourselves, is this a proposition? Is U in U a proposition? Is this something that's true or false? Let's check. Is it true? Is it true that U is in U?
Yeah.
It is? Let's think. What's our definition of U here? U is a set of all sets that don't contain themselves.
Well, if you define it as that.
Yeah. Here's our definition for U.
So U is a set.
So I say let U be the set of all sets that don't contain themselves. Now we're looking at this proposition. Is this proposition true? No. U is a set of all sets that don't contain themselves. Clearly, U contains itself if this were true. So it must be false.
That's not false either.
But if it's not the case that U contains itself, then U is a set of all sets that don't contain themselves. So then U does contain itself. So if it's false, it's true, and if it's true, it's false.
Okay. Yeah, I understand that.
So is it true? No. Is it false? No. So it's not true and it's not false.
So what's the conclusion?
So it's not a proposition.
Okay.
So this is not a proposition. U in U is not a proposition.
What is it then?
It's not a proposition.
Okay.
So all paradoxes are not propositions?
Law of contradiction. Nothing can be both true and false.
So if it's a paradox, then it's not a proposition.
Well, some people play fast and loose with the word paradox. In the strictest sense of the word, yes. So this is not a proposition. What does Axiom 1 say? The expression, that is a proposition if and only if X and Y are sets. So this is a proposition if and only if U is a set. And it's not a proposition, so U can't be a set.
So U can't be a set.
Yeah, you can't just go around defining sets into existence.
Okay, that makes sense.
It's kind of like me saying, let's consider the prime number 4. No, you can't just say that. 4 is not a prime number.
Okay.
Just because you call it is doesn't magically make it so. So I say, let's consider the set of all sets that don't contain themselves. You can't just call that a set. No. Because it breaks this rule.
I see.
All right. So there's Axiom 1, some motivation for why Axiom 1 is such an important axiom, and a little bit of history behind it. Okay, now some quick definitions. Nothing? So a quick definition. First definition is not a member of. Remember, these are only two undefined terms. So everything else I define has to be in terms of these. Sorry, we'll be given one more primitive that I didn't put here. We'll be given these primitive symbols.
Isn't that what a set is?
Yeah.
It's a pictorial representation of a set. We'll get to it when we get to it. But so far, we've talked about a set. We haven't talked about that. This is how we will pictorially represent a set. But yeah, it's primitive symbols that we'll use to represent sets. We're not going to define what those symbols mean. What those symbols mean is going to be given to us for an axiom. That will be axiom 3. Okay. I think. Yes. Okay. So some definitions. So far, these are the only two things I have. So all my definitions have to be in terms of those two things. I'm going to define just a bunch of relations. I can use a relation to define other relations. So we create the is not a member of symbol. It's the same symbol, but with a line through it. The not a member of symbol. We should leave that up as a primitive. So x is not a member of y is logically equivalent to, or it's defined to be, it is not the case that x is a member of y. Pretty straightforward definition, and I accidentally already used it once, I think. All right, next one, subset. X is a subset of y, means that for all a, if a is in x, then a is in y. Everything that's in x is also in y. That's what it means for x to be a subset of y. Good there? Yeah. Okay, set equality. We're kind of expanding what we want equality to mean. We already have equality under logic. So I already know from logic, skipping ahead, I know we don't have this notation yet, but skipping ahead, I already know from logic that the set 1, 2 is equal to the set 1, 2. I know that from logic. Because they're identical symbols on both sides of the equality sign.
Yeah.
What I want for sets is I also want it to be the case that 1, 2 is equal to the set 2, 1.
Yes.
This is not given to us under logic. But I want this to be the case in set theory. So we're extending our definition of identity for set theory. So identity still means what it means for logic, and we're extending it some. And we're still going to use the same rules for identity that we always use. Okay, here's the extension of it. We're going to call x equal to y, provided that x is a subset of y and y is a subset of x. If x is a subset of y and y is a subset of x, we're going to call those sets equal. If everything that's in x is in y and everything that's in y is in x, we're going to call those sets equal. Notice that this also makes sets like this equal. Oops, I didn't mean to do that. What's everything that's in here? Well, let's see. There's a 1 in here. Is that in here? Yes. There's a 2 in here. Is that in here? Yes. So any element you can pick in here is in here. And similarly, any element you can pick in here is in here. So these sets are subsets of each other, so they're equal. Okay. So that's equality. Our next definition is a proper subset. X is a proper subset of y. We define that to be x is a subset of y and they're not equal. So x has to actually have less elements than y. I do less because the cardinality of our set might be infinite.
Okay.
But for finite sets, x has to be smaller than y.
That everything in x is in y?
Yes. If x is a subset of y, then everything that's in x is in y, but not everything that's in y is in x. Otherwise, they'd be equal. So x is a subset of y, but x is not equal to y. So I'll write it out as a quick example here. 1, 2, 3 is a subset of the set 1, 2, 3. This is a subset of this, because everything that's in here is in here. It is not a proper subset. It's true that everything that's in here is in here, but they're equal. So it's not a proper subset. If we got rid of 3, okay, now it's a proper subset.
Okay, I see.
Or if instead we had gotten 3's and squigglies, this can be murder. Or if we had gotten rid of 1, it would be a proper subset.
So set of itself is not.
A set is never a proper subset of itself. Correct.
Why is it proper?
Because every set is equal to itself, And a proper subset requires that they're not equal. By definition. Yeah, it's a symbol that comes up a lot. So we kind of think about them as the less than and the less than or equals. But with sets. So both useful operations, depending on your circumstance. What do you care about? No, operations. Relations. These are set relations. This is either true or false. 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 These are not taking sets and spitting out sets. You're giving it sets and it's saying true or false. So these are all relations. So we defined a bunch of relations, and we defined them so far. We just have the is a member of relation that we defined them in terms of. And of course, we can always use symbols from logic to define things. That's always allowed. Because we're building on top of logic, or set theory. Okay, so no questions with those definitions. Ready for the next axiom? Yeah. Okay, axiom 2. There exists a set that contains no elements. No elements, that's it. So there exists X such that for all Y is not a member of X. Or in other words, there exists an empty set. Now we are going to do a quick proof that the empty set is unique. So that's our axiom. We're going to prove a quick theorem using that axiom. And we're going to prove that there exists one and only one set. There exists a unique X such that for all Y is not in X. And since it's unique, we can then define it, and we're going to define it to be that empty set. So this is going to be a term that we define. And if you remember from last week, when you define a new term, define a new constant, line 3 here, we have to show that it is unique. That's one of the things we have to do for it to be well defined, before we can define it. So we're defining a new constant, a new term, the empty set. So first I'm going to prove that there's one and only one set that satisfies this condition, and then we'll call that set the empty set. That's what we're doing. Make sense? Okay, how are we going to prove this? We've done 100 uniqueness proofs already. This is going to be no different. We can do it proof by contradiction. 1. Assume by way of contradiction that there exists sets, what should we call them? A and B. A, B, such that, I'm just going to say both are empty rather than saying both of them satisfy this. That's what we'll mean by empty, is there's nothing in it. Both are empty, comma, but A is not equal to B. So I'm assuming that there's two distinct empty sets. Okay. Observe that. Maybe we'll do a step here. Observe that for all X, maybe we'll say for all Y since that's what we did there. For all Y, Y in A, Y is not in A, maybe I'll say that. And for all Y, Y is not in B. That's what it means for A and B to be empty. Or in other words, Y in A is always false. And Y in B is always false. Then, for all Y, note that this is true. For all Y, Y in A implies Y is in B, which gives me that A is a subset of B. Y in A is always false. False implies anything is true. Vacuously true.
Can't you say,
So this is always true.
can't you y is not an A, that implies y is an B.
No. How would you get that conclusion? There's nothing in B. Sorry. This is a not in. Let me write that a little bit more clear. For all y, y is not in B. B is an empty set. There's nothing in there. All right. So look, by definition, what does it mean to be a subset? X is a subset of y if for any set A in X implies A's in Y. Why did I just play a show? For any set Y, if Y is in A, then Y is in B. That's always the case. This right here is always true for any Y you choose. How do I know that? Because this is always false. And false implies anything is true. So I know that A is a subset of B. Also, same thing. Also, for all Y in B implies Y is in A. Y in B is always false. False implies anything true. So that gives me that B is a subset of A. So I have A is a subset of B and B is a subset of A. Uh-oh, what's that the definition of? By definition, they're equal. Then A equals B. Contradiction. Because we assumed A is not equal to B. 6. Therefore, empty set is unique. Square box. All right, we did it. And now we can, since we proved that there's one and only one empty set, we can define that constant, and we'll define it with that symbol there. And that from here on out is what we mean by the empty set. Good?
Yeah.
Cool. Any questions with that, or move on to the next one? Pretty standard uniqueness proof. Okay, next axiom, axiom 3. This is the one that gives us that squiggly notation that we know and love. Let me just make a note here. As I'm rigorously developing this stuff, sometimes I'm going to give you examples where we jump ahead and use notation that we haven't rigorously developed yet. We're going to do that a lot. Don't get that confused in your mind. So sometimes I'm going to use examples to help you get intuition for what we're doing. And then I'm going to go back to the rigorous development. In the rigorous development, you should never let me use symbols that we haven't rigorously developed before. But when I'm doing examples to help your intuition, I'm going to jump and use whatever I can think of, however I can think of it. So thus far in the class, we haven't yet introduced that squiggly notation. This axiom is what introduces it. Okay. So axiom 3. What does it say? If X and Y are sets, then there exists a set that contains precisely X and Y. Or in other words, if I know that X and Y are sets, then I know the set containing X and Y is a set. So if X and Y are sets, then there exists a set that contains precisely X and Y. We denote it M equal to the set containing X and Y. Writing out rigorously, what did we say? We said for all X, for any set X and for any set Y, there exists some other set M such that for all U, if U is in M, then U must have been X or U must have been Y.
Yep, that makes sense.
Make sense? A little bit dense with this notation, but you gotta get comfortable with the dense notation. So I try to make it obvious to your intuition first and then jump up here. So let's try it again. Right here, M is going to be the set containing X and Y. So for all X and for all Y, there exists some M such that if for any U, if U is a member of M, so if U is one of the members of M, so this or this, then U must be X or U must be Y. That's what that dense notation is saying. The notation is, understanding the notation is as important as understanding the actual axiom. This type of notation never goes away. So we want to hammer it in whenever we come across it. They could technically be the same set. They're just any two sets. Yes. Yep, regular OR. That's the only time you'll see me use exclusive OR, and you'll never see it again. It's only useful in helping set up a proposition. Okay. So let's do a quick proof thing. Let's prove that the set xy is equal to the set yx. Or in other words, that with our notation here, this order doesn't matter. It's something I told you was the case over and over again, but never actually proved it was the case. All right, so how do we prove this? How do I prove two sets are equal? Not one implies the other. Show that they're subsets of each other. That's what set equality is, right? X is equal to y. What does that mean? X is a subset of y, and y is a subset of x. If I can show that, then it's equal. How do I show that two subsets are... How do I show that one set is a subset of another set? Yeah, I need to show everything in here is in here. The way we typically do that is we grab some arbitrary element. I grab some arbitrary element. I don't know anything about it except it's an element of that set. I show anytime you grab an arbitrary element in the first set, you grab something that's also in the second set. And so everything in the first set is in the second set. So we start by grabbing some arbitrary element from one of the sets. So let A be some arbitrary element in x comma y. I don't know which one. I just know A's in that set. Well, what does that tell us? A equals x or A equals y. How do we know that? It's the definition of what this notation means. Something is in here. U is in M. In this case, we used an A. A is in M if and only if A is equal to x or A is equal to y. So A is in here. That's only the case if A is equal to x or A is equal to y. You with me? Yeah. Now, I know that OR is... So OR is commutative. I can swap them around like you were saying. So this gives me that A is equal to y or A is equal to x. But what does that give me? That A is in the set y comma x. So if A is in this set, then A is in this set. And it turns out all the backwards logic here works as well. If A is in y or x, that gives us that A is equal to y or A is equal to x. And that gives us that A is equal to x or A is equal to y, and that gives us this. So this is actually logically equivalent to that, is logically equivalent to that, is logically equivalent to that. So I showed if A is in this set, then it's in this set, and I showed if A is in this set, then it's in this set. So I know that this set is a subset of this set. That's going the forward direction. So I know x comma y is a subset of y comma x. And I know that y comma x is a subset of x comma y, which gives me that x comma y is equal to y comma x. Square box. Follow the logic there?
How exactly did you know A equals y or A equals x implies that A is in y comma x? Because your definition doesn't have a double-sided arrow.
Thank you. That is a mistake there.
How does, it's almost like, it seems like it implies that order of that.
This just basically shows that order doesn't matter. Oh, the order makes them distinct. It's perfectly valid for me to have a set x comma x. This notation, that's perfectly valid.
Okay, but so they might be equal, another way to describe it that, I don't know how to say this. But in that logic, you're implying that x, y is different than yx.
Right here?
Not necessarily.
What I'm showing is that they're the exact same. And it's the same thing for programming. If you take some set and you stick x and then y in there, and you take some other set and you stick y and then x in there, it doesn't change anything.
Well, I know what you're saying.
And there's no guarantee of order. The computer's just going to stick it wherever it wants in memory, wherever it's convenient.
Well, I'm saying, is it possible to make a statement? They are different and they're equivalent.
No, we're saying that we are using those to represent identical things. There is no difference between them. The same way that there's no difference between, where's my squiggly line? Okay, we're still on the screen. 5 plus 3 equals 8. What am I saying? I'm saying that this is identical to this. Okay, yeah, I use different symbols to write it.
No, that's fine.
Okay. All right, so we did that proof. Any other questions on that proof? And let's get to some basic definitions. All right, so we have a set that contains 2 elements. What about a set that contains 1 element? So we define a 1-element set to be a set containing that element twice. We have this notation defined now, and so now we define this notation using this notation. We already defined this. May as well use it to define that rather than coming up with some new way to define it. Okay, so now we have a single element set. So now our notation makes sense if I want to do something like this, a set containing 1. Okay, that can make sense. And the set containing 1, 2, that can make sense. But the set containing 1, 2, 3, well now, that notation is not defined. So we can't just run wild with this stuff yet. We've only defined it in 2 cases. We know that a set containing 1 set is still a set, and we know that a set containing 2 sets is still a set. Is a set containing 3 sets still a set? Because remember, we need to be really careful. We need to make sure we don't get carried away like Bertrand Russell did. And trying to talk about things like the set of all sets that don't contain themselves. We have to be careful. Make sure that everything we're talking about is always and forever a set. So we'll get there. Quick side note that will be more relevant down the road. What about ordered pairs? So I told you everything ultimately has a set theoretical definition. Everything can be defined in terms of sets. For those of you who took discrete math, you know one of the first things you talk about with sets is also ordered pairs and lists. So let's talk about definitions of those. How do we define an ordered pair, x and y? Now this is an ordered pair, like what we use to represent a point, like when I talk about the point 1, 2 on the plane. I got this is example now, so jumping ahead using stuff that we haven't talked about. We talk about a point on the real number plane, a point on the real number plane, like the point 1, 2, or 2, 1, I mean, this point right here. We talk about that as a point 2, 1. That's an ordered pair, and that's very different from the point 1, 2. And the point 1, 2 is up right here, right? We use ordered pairs to talk about points. We use ordered pairs when we talk about set theoretical relations, ordered pairs when we talk about set theoretical functions, ordered pairs a lot. What exactly is their set definition? Here's what it is. The ordered pair xy is defined to be the set containing x and the pair xy. There's a couple ways that we can do it. This is the most commonly used one. And notice now there's no ambiguity about which one of those should be listed first. Because the left-hand element will always be a member of the right-hand element. So you know which one belongs on the left and which one belongs on the right.
A little bit confused.
And secondly, you can always find why, because you take this set and remove the element that wasn't in it. And so you can always uniquely identify the y. So let me just write a concrete example here. Uh-oh. I think this is part of this. Okay. So the definition of the ordered pair 1, 2 would be the set containing 1, comma, the set containing 1, 2. And if I just gave you this set right here, ignore the ordered pair here, you can always reconstruct what your ordered pair was. You know, your ordered pair was 1, 2, where 1 came first.
Oh, okay, I see.
And so you can always recapture this exact information if I just gave you this information. You see how it preserves it?
Yeah.
So it preserves the information. And notice that we won't bother proving this because you use stuff ahead to prove it, but notice that 2, 1 would be equal to the set 2, comma, 2, 1. And this set is very different from this set.
Yes.
So the order pair 1, 2 is not the same thing as the order pair 2, 1. And so the order pair x, y is equal to the order pair a, b if and only if x is equal to a and y is equal to b. Two ordered pairs are equal if and only if both their left-hand elements are the same thing and both their right-hand elements are the same thing.
I see that.
Okay. And then ordered pairs that have more than 2 elements, that have an arbitrary number of elements in it, so 3 or 4 or 5 elements, we call them lists. And the special case where a list only has 2 elements, we call it an ordered pair. I'm going to say ordered pair a lot. It's a pair of numbers, or a pair of sets, a pair of things, where their order matters. In sets, order doesn't matter. Here, order does matter. Now, how do we find an ordered triple, like x, y, and z? We define that as the ordered pair of these 2 sets. Notice now this is just a set. What set is that? That's that set right there. So we have set, comma, set. And so we would define it exactly the way we defined it up here.
You still don't have a case where you have a second.
Correct. We still don't have a set containing 3 elements. And so we could create some recursive definition now for 4 elements. What's a 4-element tuple? It's an ordered pair with a 3-element one and a 1-element one. I mean, what do we mean by the set A1, A2, A3, and A4? Let's not do subscripts. Makes it too big. What do we mean by the ordered foursome of A, B, C, D? We define that to be the ordered pair where the first ordered pair is a triple. A, B, C, comma, D. And what's that ABC? We defined it right here, which is defined as these. And what's that? We defined it right here. So plug that in for that. Then we can plug that back into the definition. Then we can plug that back into the definition. And we have a set of 2 sets, a side of a set of 2 sets, a side of a set of 2 sets, a side of a set of 2 sets, with all the way back.
Yeah, but doesn't the product of that be more than 2 sets?
Doesn't the product?
X, Y, Z, that's 3 sets technically.
All right, let's write out one of these. So I'm going to write out this one as sets. You with me? I don't want to write out that one. It's going to be too big. All right, so what is this? It is the ordered pair x, y, comma, x, y, end it, comma, z. So this is this, right? But what is x, comma, y? So this is equal to the set x, comma, y, comma, z. So now it's this order pair. One set, 2 sets. Now what exactly is this? Plug it back into this definition. This is equal to, we have the set containing the first element. Here's our first element. The set containing the first element, x, comma, y. The set containing the first element, followed by the set containing the first element and the second element. So the set containing the set x, comma, y, in parenthesis, comma, z, in parenthesis for this, and then in parenthesis for this. Okay. And you'll notice that in between all our curly braces, we never have more than 2 elements. We either have 1 element in there, or I think we always have 2 elements, right?
Yeah.
2 elements, 2 elements, 2 elements. So it's always 2 elements, which is notation we have defined. So we can define now an n list, however long we want, just using 2 element sets over and over again. And that's all notation we needed.
Okay, I see it now.
Okay, there's it completely written out. And you can see why I don't want to write this one out. And get atrocious.
The order pair set definition is still kind of fuzzy. I understand the concept of like, okay, two sets of x, a set of x and y. And then you went on to say how like, okay, well in this case, it was just, yeah, it was fuzzy. Like I understood that you were performing some like subtractions of sets if that's in terms of order.
Here's what we'll do. I'm going to give you a set. I'm not going to tell you the order. You figure out the order from the set. What order pair is that?
Obviously, I can intuitively just say 2 and 1.
2 and 1.
That doesn't, it's not explicit.
The point was we came up with, even though this is an unordered collection, it preserves ordered information.
So, okay, so all right, so if I would just go through it.
So the point is you can do that.
If I was to go through it logically, I could say, okay, obviously, well, okay. So the first number, symbol essentially, is the symbol in the set, not a set.
Not necessarily the first. Look, let me give you another one and you could have figured it out.
I get that I can figure it out. I'm just wondering how you describe it. Like, I don't know how I would intuitively even know that just by looking. Unless you weirdly explain.
Here's another way I could write the set.
Yeah.
What's the order pair? It's the order pair 2, 1. How do you know that? Here's your elements. Here's one that comes first.
Meaning I'm looking for element in the set. It's not a set. It's the first.
Oh, yes. So one of these is always a subset of the other. Or sorry, one of these is always a member of the other. This is in here. This is not in here.
Yes.
So the one that's a member of the other is the one that goes first. But the point is, the only point is that, look, it preserves the information. And so if you can always tell, that means there's some systematic way of doing it.
My brain is already figuring out logically without me actually understanding why. Like I can't actually describe why, other than I can say, okay, first letter is the element in the set, it's not a set. And then I can say, okay, and the second letter is the element in the inner set that's not an element of the outer set.
So the only point is, for any two sets x and y, if I give it to you like this, you can always go back to it this way.
But what I just said is correct, isn't it?
I don't know. I didn't follow it.
Okay. If you have a set of an element and a set, first one is always a set with the element that's not a set, and then the second one is always a set.
You can't talk about order. Oh, you're saying the first one that you put over here.
Yeah.
Yes.
And then
One is always, I have a set of two things. If it represents an order pair, one is always a member of the other.
one is always a member of the other.
Yes. This is a member of that. That is not a member of this.
Yes.
So one's always a member of the other. The one that's a member comes first, and then the remaining member comes second. Because this only has two members.
The remaining member, okay.
Yeah. But doesn't matter. The point is, you knew that you could do that. So we're not losing any information. And so using unordered collections, we can still come up with ways to preserve order in unordered collections. And so even with sets, we can create order pairs. Even with sets, we can create order triples. You can create any list of numbers however big you want, and I can store it in sets. It might be atrocious to write it out here, but we can do it. This is the point. So we're not trying to sit here and be economical about how we use sets. We don't care. All we care, is there a way to do it? Good. So we can do it. So that was the point with this is help you see that any list can be stored as sets and written as sets, because that's a mathematical logic that we use a lot. And one of the things I want you to get intuition for as we go through this is every single mathematical object has a set theoretical definition. It can be ultimately defined in terms of sets. So I want to establish that intuition as we go. All right, let's move on to our next axiom, our axiom of union. Now, let's just do a feel-good example first before we go through this axiom. Because you guys are used to seeing union written out this way. You're used to union, the set 1, 2, union, the set 3, 4. And you want to say that's equal to the set 1, 2, 3, 4, right?
Yeah.
Here's the way we're going to do it. In set theory, we write the union this way. We write union, and then we put all the sets we're unioning together in a set. So I have some set containing all the sets I want to union together. So the union of this set means what we're used to, means collect all the elements from each of its elements. So union, a set, means collect all the elements that were members of this thing's members. This thing right here, we're going to call X. So X is going to be a set of sets. And this thing here that we spit out when it's all said and done is going to be M, what we call M. So M is going to be equal to the union of X, like what we have right here. M equals the union of X. X is going to be something like this. We're going to union up the elements of X, and that's going to give us M in this axiom. So there's pictorially what we're talking about. Now let's jump to the axiom. If X is a set, like this, then there exists some other set M, like this, whose elements, the elements in here, are the elements of X. The elements of this set are the elements of X. 1 is not in X. What's inside of X? The set containing 1, 2, and the set containing 3, 4. That's what's in X. 1 is not an element of X. 1 is an element of X. 2 is an element of X. So read this one more time and hope it clicks. If X is a set, then there exists a set M whose elements are the elements of X. And we denote that set M as equal to the union of X. Any questions on that one? It's just a little bit weird for how we're used to defining union, but it's pretty straightforward once you see it.
So there's pretty much no concept in set theory of object that isn't a set.
Set theory only works with sets. It only talks about sets. Correct.
Like,
It's just sets inside of sets inside of sets inside of sets. It's all sets.
at a certain point, you're just going to be dealing with the empty set. Like if you were to reduce that, saying if you were to break everything,
Yeah.
it'd all just be sets.
A lot of it we just construct. We got the empty set, and then we got the set containing the empty set, and then we got the set containing the empty set.
That's it.
Well,
how are you supposed to capture other knowledge or other information?
isn't it amazing that we can just keep doing this with sets?
I mean, like you were trying to capture the idea, the set of all shirts that are blue.
Well, it has to be a mathematical object somehow. So somehow you got to take shirt and convert it to a mathematical object. And so you might take that shirt and give it some ID number. And that ID number references a shirt, or whatever you do.
Yeah.
And then the ID is going to be some number. That number is going to have a set. And so it can be expressed as a set. Okay. Writing out now. Let's reading this axiom 4, but with our dense notation. Got to get comfortable with this dense notation. What does it say? This again. It says that for all x, there exists an M, such that for all y, if y is a member of M, if y shows up in M, then there must have been some set u in x, such that y was a member of u. So here's my u in that case. Let's read that one more time. That's pretty dense. For all x, there must exist an M, such that for all y, if y is a member of M, so y is 1, 2, 3, or 4, then there must exist a u, such that u is a member of x, so u is going to be either this or this. and y, whatever we picked here, is in one of the u's. That's what the axiom says. All right. Some more, huh?
Does that only allow you to do 4 elements? So,
4?
yeah. Like, what would you do if?
Oh, this notation here is bad notation. This was just an example. We haven't defined this notation.
I know, but in your definition there, it still doesn't allow for a 3-element set, does it?
We don't have notation to write out a 3-element set, but we're in no way restricting our sets. What's in our sets, we don't know.
I'm saying is Axiom 4 doesn't necessarily give you a way to write a 3-element set.
Not yet. We'll define that notation here, in, like right now. Okay. So, because we use unions to define these things now. Union, this was our axiom for union, and obviously unioning sets together is one of the major ways we build bigger sets. So, a quick example. If X is equal to the set containing A, if X is equal to the set containing A and the set containing B, where A and B are sets, then what is the union on X equal to? Just a set containing AB. Nice, simple example. Okay. Now let's create a definition. Let A, B, and C all be sets, and let X be the set containing AB, comma, and C. We define that notation to be the union of this set. Notice that this notation is well defined. So we just define new notation in terms of existing notation. Probably would have been better if I just wrote it all in one go. Can't go off the screen there because we'll move the camera. So right out over here, what am I saying? I'm saying we define now the notation ABC when we want to put 3 things in there. We're defining that to be the union on the set AB, comma, C. The union of these 2 sets. And so now we define some new notation.
You don't need an axiom for that?
Now, we know that as long as these 2 things are sets, their union is a set.
Yeah, but the union of that set would be.
I'm just coming up now with a pictorial way of writing it. And so here's my new pictorial way of writing it.
How does that match your set? You only have
This tells me that for any set, I can union its elements. That's what the axiom says. And it will still be a set. So we're assuming that A, B, and C here are already sets. So I know those are sets. Now the set containing AB, that's a set. The set containing C, that's a set. We define that notation. So this is a set and this is a set. So this is the outer set is a set containing 2 elements, which is valid notation. And so we define this new notation in terms of existing notation, which is how you define things. And so now we know what it means to write out a 3-element set.
Oh, I'm sorry, I was reading your thing there wrong.
Yeah, sorry, hit a crappy spot on the whiteboard.
No, it's not because you're writing, it's because I'm just doing it.
Oh. Okay. So everyone good with that definition? Now I can write out 3 elements. Now we're going to create a recursive definition. Let A1, A2, AN all be sets. We define the set containing A1, A2, AN to be the union on the set containing the first AN minus 1 sets together with the AN set. Kind of dense notation there. So let me write it out for a concrete number. We'll do it for a concrete number. We'll do it for, should we just do 4? Don't want to get too high. So we're saying the set containing A1, A2, A3, A4. Any 4 random sets. All we know is that A1, A2, A3, A4 are all sets. This notation, we are defining it to mean, by definition, this is equal to the union on the set A1, A2, A3, together with the set containing A4. Now notice that the set containing A1, A2, and A3 is we already have defined. That's defined right here. So if you want to write this out even more fully, I guess, you could write this as the union on the set, this set can be rewritten as union on the set A1, A2, A3. Now this one. So union those, and then we put together A4 here. Okay, there it is completely written out. You're unioning together these 2 sets. But what is this set? It's the union of these 2 sets. So by definition, we can replace this with this. And then by definition, we can replace this whole piece with this.
So essentially, axiom 4 is saying you take a set of sets and pull out all the elements out of the inner sets and put them into all in one set.
Essentially.
That, okay. It just. Okay.
Dense notation. A lot of squigglies, dense notation. Notation, something that with time you just get used to it.
It's really hard. I look at sets as really like an object or like a mind. And essentially, they're like, it's like they just, I don't know how to describe it.
Well, while you're thinking about that, I didn't know. This definition only holds where n is greater than or equal to 3.
Okay, so here's the limitation. All the elements in the set have to be a set.
Correct.
Okay, that makes sense.
Sets only contain sets. It's all sets.
Just count how many times you say sets in this class.
All sets.
All sets, all the way down. Can't remember the physicist in the story, but some story where the physicist is talking about the universe and explaining how the Earth is just there and it's not supported by anything. And when it's all said and done, some old lady's getting after him, saying that, no, we know that it's really on the back of a turtle. And the physicist asks, what's the turtle standing on? She says, very clever, nice try. It's a turtle all the way down. Sets all the way down. Sets aside, sets aside, sets aside, sets. Can't get away from them. Non-set theory, at least. Or any field of mathematics that uses it. Or any field of physics that uses mathematics. You can go get an American literature degree or something. I don't know. Okay. We finished that definition. Okay, now we're getting up, working our way up to the hardest axiom here, axiom 5. That's the weirdest one, so a couple definitions that we're defining just for the sake of working up to this axiom 5. One definition. A relation R, remember what a relation is, predicate that takes 2 terms. A relation R is said to be functional provided that for every x, there exists one and only one y, such that x is related to y. Those of you used to set theoretical definition of a function, that's exactly what we mean by a function. So a relation R is said to be functional provided that for every x, there exists one and only one y, such that x is related to y. As an example, we can think about R as being the doubling relationship on real numbers. So if it's the doubling relationship, then 2 would be related to 4, since 4 is double 2. And 3 would be related to 6. And 9 would be related to 18. And for any number I give you, you can give me one and only one number that it would be related to under the doubling relation. So the doubling relation would be an example of a functional relation. It's one such that for every input, sometimes we call the left-hand side the input, you get one and only one output. And we'll have a lot more to say about functions later on, but yes, it's just going to be a more restrictive notion. So we have a notion of a function from just logic, and then we have now this notion of a function as a special case on a relation, and then we're going to have a set theoretical full definition of a function. And it's just more and more restrictive. Everything we talk about a function in terms of the way you're used to thinking about a function is still a function in terms of all these other sets. The way that you think about a function, does it satisfy this?
Yes.
Yes, it just also has more structure, like a set for its domain and a set for its range.
Well, that's implied in that, isn't it?
We're getting there. You'll see what I mean by we're getting there.
Is it on the board somewhere?
It's in Axiom 5.
Okay.
Axiom 5 is what is going to ultimately give us our set builder notation. And it's that set builder notation that you want to use to start defining those things. Yeah. Okay. So a relation is said to be functional provided that for every x there exists a unique y such that x is related to y. All right. Next definition. Let M be a set and let R be a functional relation. Then the image of R on M, written as Im space R, and we're passing M into R. So here's the way that we're going to write the image of R on M. We think about R as some sort of mapping, M as the input, and it's going to give us some output, which we call the image. So the image of R on M, written as M R on M, consists of all the y's for which there is an x in M such that x is related to y. Let's make sense of this with an example. So we pick M to be some set. Doesn't matter what set we pick. We'll do set 1, 2, 3. Okay, now we got to pick some functional relation R. I'm going to pick the doubling relation R. You with me?
Yes.
Now I'm going to write it a funny way. R, for any input x you give it, it spits out 2x. It doubles whatever you give it. For anything you want to know, what am I paired with, plug it into this formula and it tells you what you're paired with. So with R, what is 1 paired with? It's paired with 2. When we plug 1 into this, we get 2. Or the double of 1 is 2. R is the doubling relation. When we plug 2 into R, what do we get? And when we plug 3 into R, what do we get? So M was a set of all the inputs that we put into R. All the outputs that came out, all the things that it was paired to, we paired to 2, we paired to 4, and we paired to 6. The collection of those things we're going to call the image. So the image of R on M, the image of these things on this relation, consists of all the y for which there is an x in M such that x was related to y. In other words, we had 1 related to 2. That's what we had written here. We had 2 related to 3, or 2 related to 4. And we had, over here, 3 related to 6. So our image consists of 2, 4, and 6. So our image is going to be 2, 4, 6. That is going to be the image of this relation on this set.
Okay. I see.
Now I just wrote that as a set. I have to justify that still. It consists of those things. How do I know that those things are a set?
Is that what Axiom 5 gives you?
That's what Axiom 5 is going to say. It's going to say when you do this, that thing that consists of is a set. That's all Axiom 5 tells you. A surprisingly powerful axiom. All right. So let M be a set. Let R be a functional relation. Then the image of R on M is a set. All the things that came out, when you grab them together, it's a set. So the image is a set. That's all Axiom 5 says. Any question with any of those two definitions or that axiom before we move on to define some new notation?
Think that makes sense?
Okay, here's notation that we already skipped ahead and used before in logic, but let's define it again here. When we say that for all x and y, some proposition about x is true, that means for all x, if x is in y, then that proposition is true of x. For all x and y, p of x is the same thing as for all x, if x is in y, then p of x. Good?
Yeah.
Just defining this new notation for all x and y. We haven't done that notation before. We kind of did. I would accidentally do that, say, for all x in the real numbers. I kept writing that over and over again. Similarly, there exists an x and y such that p of x means that there exists an x such that x is in y and p is true for x. P here is any predicate.
Is there a logical definition for Axiom 5?
Logical definition for Axiom 5?
Not a logical definition. A way of writing Axiom 5 is logical. Just like you have on the evidence.
Not that I can think of, because the only way to do that would be like set builder notation. Be like the image is a set of all these things, and use set builder notation to define what it is. But Axiom 5 is ultimately what's going to give us our set builder notation.
Set builder notation.
Set builder notation. We are about to do set builder notation right now. We're going to define it, but it turns out that Axiom 5 is what we need to do, set builder notation. Oh, I have a theorem here. Let Px be a predicate and M be a set. Then the elements y in M such that P is true for y constitutes a set denoted by, oh, we do set builder notation from this. Okay. Let me motivate this a little bit better. Axiom 5 we hardly ever use directly. We use Axiom 5 to give us this theorem. The theorem is usually what we use directly. The theorem is a little bit of a weaker notion than Axiom 5. So for other reasons, we need Axiom 5 as opposed to just this theorem. But this theorem, which is a more restricted notion of Axiom 5, is what we typically use Axiom 5 for, and we're going to use this all the time. And it's the theorem that gives us set builder notation. All right, so let me walk you through it. We're proving one more time because I had to remind myself of what we're doing. So let P of x be any predicate and M be any set. Then the elements y in M, all the elements y in M such that y satisfies that predicate. That predicate might be the is blue predicate. Or maybe we'll think about these in terms of number. Maybe P is a is even predicate. And maybe M is, I don't know, the set numbers 1 through 10. So the elements y in the set 1 through 10 such that y is even constitutes a set. So if I take all the members of y, all the members out of n that satisfy some condition, when it's all said and done, I have a set. So I've got some existing set. Now I say I'm going to take all the members out of that existing set that satisfy some condition. the result is still a set.
Isn't that very similar to Axiom?
I'm using Axiom 5 to prove this.
Okay, I'm following.
So this is what we're going to prove. And that new set that we're talking about, we're going to denote this way. It's going to be the set of all y in M such that P is true for y. Very clear what we're doing here. M some set, P some condition that maybe the elements in M satisfy or don't satisfy. We're filtering out all the members that satisfy P. And after we do that filter, what we're left with, still a set. That's what we're proving. Okay. So, 1. Observe that either nothing in M satisfies P, or something does.
At least one thing, right?
Yeah. Or something does. Maybe I should have just said that out loud. I don't want to take too much space writing all that. So we have one of two cases. So M is a set of some things. Let's write a concrete example down here to help us think. M is a set of some things. Maybe it's 1, 2, 3, 4. And maybe P is the P of X is the X is even predicate. With me? So either one of two things happens. Either nothing in M satisfies P, nothing in M is even, or something in M is even. Right? Has to be one of those two cases. Okay, so 1. If nothing, let's say it this way. If it is not the case that there exists some y, maybe I'll use z, thinking ahead. If there does not exist some y, does not exist some z in M such that P of z, then we define the set of all y in M such that P of y to be the empty set. So we're defining this notation to always be a set no matter what. We're defining set builder notation. That's what the theorem's out to do. So if nothing in M satisfies P, so maybe the P predicate in that case was the is greater than 5. Notice that nothing in M is greater than 5. So then the set of all y in M such that M is greater than 5 would be equal to the empty set. That's what we're defining it to be in the case where nothing in M satisfies a condition. That's what this first line is saying. If there does not exist some z in M such that z satisfies a condition, then we define for all y in M such that P of y is true to be just the empty set. On the other hand, 2, if there does exist some z in M such that P of z is true, then here's where we do something crazy. Then define R such that R on xy is equal to, so let's see, xy is in R. We want that to be the case when P is true for x and x is equal to y, or it is not the case that P is true for X and Z is equal to Y. I think that's right. This seems super unmotivated. We're going to make this make sense here in a second. So I defined some functional relation R to be this. So 3, then it turns out that what we define this notation to be is just going to be the image of R. And then I'll make that make sense. So then the set of all Y in M such that P of X is true, it turns out we're going to define to be the image of R on M. Now let's make sense of that, because this is super unmotivated. Let's go back, concrete example to help us think about this. So M we'll do once again as a set 1, 2, 3, 4. And P, what should our predicate P be? We need to be something that's true for this. Maybe we'll extend this to 5, 6, and we'll do the is even. P of X is equal to, P of X is equal to, it's the is even predicate. X is even. Okay, so let's get a feel for this relation. This functional relation R of xy. So R of xy. Let's first off plug in 1. See what 1's paired to. Because R has to pair everything in M to one and only one thing. R is a functional relation. So I set it up so that everything in M is going to be paired to one and only one number. And let's see what they're all paired to using this functional relation. You with me?
Yeah.
Okay. So maybe I'll just write it this way. What is 1 related to using our functional relation R? Well, let's see. So in this case, we're saying if X is 1, then X is related to Y if and only if the proposition is true for 1. Sorry, we missed a piece. We only define this if we know that there is something in M that satisfies our predicate. So I only define this relation if there exists Z in M such that P of Z is true. So we said in our pretend example, M is 1, 2, 3, 4, 5, 6. Our predicate is X is even. What should we have our Z be? We need to pick something out of there that satisfies it.
Anything?
Anything, doesn't matter. Because the way I defined R, notice that I used Z in my definition of R. And what do I know about Z? It was something in M that satisfied our predicate. So 2 works. So we'll have Z equals 2. Let's make a note of that somewhere here. Z is equal to 2 in our example up here. You with me? So now let's see what 1's paired with. So let's see. Is 1 even?
No.
No. So this is false. So ignore the rest of this. So, or, is 1 not even? Yes. Then our Y has to equal Z. So 1 is related to 2. So we pair 1 with 2. If X is 1, then plugging in 2 for Y is the only thing that will make this true.
Why not like 4? Yeah, but
Because our Z was 2.
well, why not make Z 4?
I said, give me the Z first. Because we can only define this function once we have a Z.
Okay.
If Z is a member of M that satisfies the condition, pick any one you want.
I have to pick.
But you need to give me one in order for me to define R. I'm defining R after you give me a Z.
Why is it the case that that one of those statements has to be true?
I'm saying X is related to Y if and only if this happens.
But why is 1 related to 8?
Look, I basically need to try every possible x and y and chug it through the thing. And if plugging in a particular x and y makes all this true, then x is related to y. So I need to try 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. I need to try 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6. To see which ones make this thing true. If we plug in 1 for x, the only value we can possibly plug in for y is whatever our z was, in this case 2. Right? So 1 and 2 make this true. Why not 1 and 4? Let's look at 1 and 4 for a sec, shall we? So we plug in 1 for x. Let's see. Is x even? No, so we can't satisfy this part. So we have to satisfy this part. Is x not even? Yeah. Is 4 equal to z? No. True and false is? False. False or false is? So 1, 4 does not satisfy this relation. 1, 2 did, 1, 4 doesn't.
Why is that useful? 1, 6.
I defined a relation such that its image is going to be exactly the set we care about. I'm defining this notation. And so I'm saying, I'm defining this notation to be some set. So I need to use something that I know is a set. Axiom 5 gave me that this thing is a set. This is, this right here is the hardest part of what we're going to be doing in set theory. It's a big pill to swallow, all for set builder notation. So all we're after here is to define our set builder notation. So I can say the set of all y in M such that some condition satisfied. You could have made it a definition. You could have made it an axiom itself, but it turns out it's more restrictive than what Axiom 5 gives us, and we need the extra oomph that Axiom 5 gives us.
You didn't want to add another axiom.
Right. Don't add as a separate axiom because it's entailed by Axiom 5.
Why?
It would be a non-constructive axiom.
Yeah.
Well, sometimes we have non-constructive. Well, axioms.
Never. Definitions or theorems. Never non-constructive axioms. An axiom is non-constructive. We don't add it as an axiom.
So explain to me why, for instance, we add the axiom of time. We could technically derive it from clef.
You can't. Using just the axioms on the real numbers, just plus, define a function for times.
Then you can't do that.
You can't do it. And you can use our techniques that we had from last time to prove how you can't do it. And that would be to come up with the interpretation where all the other axioms are true, but the axiom for multiplication is false. If you can come up with an interpretation that does that, then that axiom couldn't have been entailed by all the other axioms. Otherwise, if they were all true, then that axiom for multiplication would have to be true as well, if it could somehow be derived from them. Now, I don't want to write out the axioms and come up with an example here, but
I know. And I probably should have asked that, but yeah, that's interesting.
you're used to they tell you in early schools, oh, we think about multiplication as really fast addition. And that's a nice intuition to help a kid think about it. But no, that's not what it is. Multiplication is not just fast addition. Multiplication is multiplication. And there's a drastic way that they differ. The empty product and the empty sum. The empty sum is 0, the empty product is 1. And if an empty product was really just in terms of sums, then it would be an empty sum, and so an empty product should be 0. But it's not, it's 1. Go plug 0 factorial into your calculator. Spits out 1.
So you're saying times, so an intuitive way to look at it is.
It helps kids' intuition.
But
That 5 times 4 is doing 5 plus 5 plus 5 plus 5 4 times. That's great intuition.
but it's not.
But to say that multiplication is just really fast addition,
Can you give us an example?
of
Well, it seems like when you use multiplicative inverses, that's not really related to addition at all.
right, and then they also say, well, then you're dividing, and that's subtracting. And then I don't know how you're supposed to make sense of something like 24 to the 1/2, but hey, I'm sure there's some way to rationalize it.
Well, I could even see, like, take for instance, purity. You can't really describe an axiom. For instance, if let's say the definition was that it was 2 times 3 was, or no, let's say 3 times 4. It's it's x plus x plus x plus x, or something like that. It's such a variable change in the axiom definition because, well, maybe there's a way to describe that. I'm not sure. But
Multiplication needs to be given in its own axioms. It's
I
fundamentally a different operation.
I'll look into that.
But all right, let's go back to this monstrosity and trying to wrap our head around it. So I was giving you a concrete example. So we're looking at this relation where P was is even. Our M, everything that we're taking our elements from, are the set M, 1, 2, 3, 4, 5, 6. So all the x, y's, and z's here all have to be elements from this set M.
What happens when you plug in an even? Because we were plugging in odds, but what about even?
Right, so so first thing I wanted you to see is the only number that 1 can be paired with is 2.
Yes.
Since 1 is odd, this is always going to be false. So our only hope is to make this true. When is this true? When it can't be true unless y happened to be the same thing as z, which was 2. So 1 could only be paired with 2. Okay, now let's look at 2. What's 2 paired with? What's 2 related to? Let's see, plug 2 in here. Is 2 even? Yes. So then if we want to satisfy this, our y has to be equal to x. But what was x? 2. So the only thing it can be paired with is 2.
Okay.
To make this true. Because now this is going to be false every time over here. Because 2 is even. So this one's always going to be true, so this one's always going to be false. So this whole thing is going to be false. So if we want this whole thing to be true, our only hope is to make this thing true, which means we have to make this thing true. So in that case, our y had to equal our x. So if 2 was our x, the only value we can plug in there to keep this true is 2 for our y.
Okay, what about 4?
Let's do 3 really quick. What's 3 related to? Let's see, is 3 even?
No.
Nope, so ignore this side, so we have to make this side true. Is 3 not even?
Yes.
Yes, so the thing it's paired with has to be z. What was z? 2. So 3 is paired with 2. Okay, now what's 4 paired with? What's 4 related to? Well, let's see, is 4 even? Yes, so ignore this side. So what does y have to be to keep this side true?
4.
4.
So,
And so everything that satisfies the relation, we just pair with itself. And everything that didn't satisfy the relation, we just pair with z, whatever z was, which was the thing that satisfied the relation. So all the right-hand sides are going to be things that satisfy the relation.
because all the left-hand sides get paired with something on the right-hand side.
Right, we're forcing all the left-hand sides to get paired with things on the right-hand side. But notice that we're going to get everything in M that satisfies the relation on the right-hand side. If something in M satisfied the relation, then it gets on the right-hand side from this. So 2 will show up on the right-hand side for sure, because it's going to be the right-hand element of 2. 4 is going to show up on the right-hand side, because it's going to be the right-hand element of 4. 6 is going to show up on the right-hand side, because it's going to be the right-hand element of 6. And all the other ones, they're things that don't satisfy the condition, just map them into something that does. We don't care what, just something that does. We would have already accounted for it over here. So the fact that we paired 1 to 2, we already knew that 2 was going to show up in our image here. The fact that 1 also paired to 2 doesn't help 2 show up in the image. We already knew it was eventually going to. The fact that we paired 3 to 2 doesn't matter. Because we knew 2 was going to give us 2. And we knew 4 was going to give us 4, and we knew 6 was going to give us 6.
Okay.
And so you can replace our z here with 2, 4, 6. It doesn't change anything. It just changes what all the odds go to. All the evens already got us all our evens.
That makes sense with this example. I know it's a lot of work, but would you be willing to give another?
Yeah, we can do another example.
Like keep M and just change the P.
All right, so we'll do M. You want to keep it the same?
Yeah, 1, 2, 3, 4, 5, 6.
1, 2, 3, 4, 5, 6. We'll make P of X is the X's prime.
Okay.
Now think on a high level what we're after. Our set builder notation here, we want all the y in M such that y is prime. We want some way of getting everything out of the set that's prime. What I'm arguing is that all the right-hand elements for our relation here are going to be those very things. So I need to make all the primes show up as y's in this relation, so that they're in the image.
But before we can do that, we need to take the z, right?
Right, so we only define this if there is something in this that's prime. If we would have done, so if P of X would have been X is, if we would have done P of X is equal to X greater than 10, so if that would have been our P of X, nothing in M satisfies it. And so our set builder notation would have been defined to be the empty set. So if nothing satisfies it, it's just the empty set. If something satisfies it, give me some arbitrary thing that satisfies it, I don't care. I know something satisfies it, call it Z. Z is something that satisfies it. In our case, it could be 2, 3, or 5. Doesn't matter which one. Just pick one. Let's pretend it was 5. So now our relation, what does it do? Our relation takes 1 and pairs it with, let's see, 1. Is 1 prime? No. Is 1 not prime? Yes. So 1 gets paired with our Z, 5. 2. 2. Is 2 prime?
Yeah.
So what does it get paired with? Itself, 2.
Okay, I see it.
3. Is 3 prime?
No. Oh, yes.
Yes. So 3 gets paired with 3. 4. Is 4 prime?
No.
So it gets paired with 5. 5. Is 5 prime?
Yep.
So it gets paired with 5. 6. Is 6 prime? No. So it gets paired with 5. Notice all the right-hand elements are the prime. We have 5, 2, 3, 5, 5, 5. All the ones that weren't primes, we just paired with some random prime, 5. And all the ones that were primes, we paired with themselves.
So it doesn't matter how you define your P.
It doesn't matter what the Z is. Oh, the P is just acting as a filter. All we had to do was come up with some convoluted way of making a function such that all its right-hand elements were the things that we cared about from M.
Yes.
So this is just some contrived way of coming up with that function. You can try and come up with a better one.
Is there a better one?
I don't know. That's mine.
Okay, that helped me, thank you.
Okay, so then that set, because we know all these right-hand elements, we call that the image of it, is a set. So the image now of our functional relation R on M is the set 2, 3, 5. It's all those right-hand elements. That's the image, right? So that's what we mean by the set of all y in M such that y is prime. We mean 2, 3, and 5. And you would have already guessed that. I just need to prove that that's actually a set. And that's always a set. Because we can always go through this construction. For any M and for any P you choose, I can always re-go through this construction and its image will be a set. And it will be the set we care about. All that is a terribly long way of saying now we can use set builder notation. And so now if I know M is equal to set 1, 2, 3, 4, 5, then I know that the set of all y in M such that y is even is a defined set. And we know what that set is. That was 2, 3, 5. And so now we can use notation like this.
So does that mean?
It's just giving us set builder notation. Y is, oh yeah, prime. But this was just a stand-in for some predicate. Yeah.
Does that mean that you can't use that other notation to represent the empty set? No Z check against.
We can't use set builder notation to represent the empty set? Sure we can. That's up here. If it's not the case that there was a Z in M that satisfied it, then we define the set of all y in M such that
I forgot that we did that.
be the empty set. And I don't know if we formally get it from our system so far or not, but we also let ourselves write the empty set this way. I don't know if we have that somehow up here, but if it's not somehow entailed, we can add that as our own little special notation. Okay, so that was far away the hardest part, and all it gave us was set builder notation, which is very, very useful. Now, notice how our set builder notation works. Our set builder notation is the set of all y in M such that y satisfies some condition. We cannot do what Bertrand Russell was trying to do. We cannot just say the set of all y such that y satisfies some condition. This is what we did in naive set theory. We have to do the set of all y in some other set. And so we always have to be picking elements out of a set. We can't just say all the things out there that satisfy this condition. Because then we might not be talking about sets anymore. And it's through his liberal use of this notation that he got himself in such a pickle. You'll notice when we define the set of all sets that don't contain themselves, we gave it one of these types of definitions. We said U is equal to the set of all x such that x is not in itself. So it's in using set builder notation this way that we get in trouble. We can't do that. We always have to use set builder notation to be U is equal to the set of all x in some other set, M, such that then some condition satisfied. And that way we're guaranteed that we're always talking about sets, because it came from some set. And only sets can be in sets. So it's what keeps us always talking about sets.
So that's how he fixed his self-reference. This actually kind of changes that.
He didn't fix it. Other people developed this axiomatic set theory. His set theory was just wrong. So it's not like he went and tweaked it here or there and now it's good. It was, I mean, it captures a lot of the same similar ideas. And in some cases, we think we're not going to be too strict, so we'll use Bertrand Russell's notion of set theory for what we're doing, because it's inferred from context what the set is when we use some notation like this sometimes. But no, it's not like he tweaked his logic and it works. There was a problem. And it was a new system that was built that fixed the problem. I've never personally gone through his Principia Mathematica. They're massive. And
So
since it doesn't work in the end, I never thought it was worth the effort.
So it's never fixed in those volumes.
No, it's not fixed in those volumes. Yeah, it is too bad. Yeah, it's too bad. Because it turned out it wasn't just a tweak to the system. It was fundamentally the way they went about constructing sets you just can't do. Yeah, I think they have 3 volumes. Is it 3 volumes that those guys wrote?
If I remember right, they stopped partway through the 3rd volume.
Maybe.
I could be wrong.
I know it's more than 1 volume.
Yeah, at least 2 that are published. I think we started with it.
Yeah, so. But hey, help clear up some stuff.
Have to do something wrong without that.
I guess it really helps the people that can after them.
Walk around the shoulder.
Yeah, and I mean, they gave us, I assume, some of this naive set builder notation they gave us, and we still use it all the time. So, yeah, I think it helped clarify a lot of ideas. It's just now you can't actually use the book that they wrote as an actual textbook. It's just they helped other people write better books. Okay. What's here? And that was just example stuff. How are we doing for time? How are you guys doing? Did that kill you? We want to take a break? I promise it's getting easier. But it might not be bad to re-pick up there next time and force you to re-go through all that. I don't know. How you guys feeling? Want to keep going? Or yeah, getting through all of it, that's a stretch. You gotta go. All right. Yeah, we can call it there and continue with set theory next time. And re-go through that beast next time.